Supposing you're trying to design a tube amplifier. They call them valve amplifiers in Britain. And you've either decided to go old school and go back to the Radiotron Designer's Handbook, or new school, and you've used a more modern text on designing amplifiers like valve amplifiers. This is the 4th edition by Morgan Jones. In any case, one of the decisions you'll have to make is which tube to use. In each stage of the amplifier, the question is, for example, would a 6SL7 be better than a 6SN7? And to do that, you can use the data of the published by the tube manufacturers back in the day. But if you're using new old stock tubes, like these are, by the way, they're getting pretty expensive these days if you haven't looked at the prices on eBay. Some of these new old stock 6SN7s, particularly the ones that are especially collectible, run over $100 each. At any rate, but you aren't just happy using data that somebody put in a book back in the 1950s. You'd like to actually know what your 6SN7 or 6SL7 will do. Well, that is a place where a curve tracer would come in handy. Now, back in the day, curve tracers could be found in most tube design labs. They were used both by the people who designed the tube itself to see how well they had done in meeting their design objectives, as well as by the circuit designers to see which tubes they would use and exactly how they would design the circuitry around them. So, with that as motivation, let's take a look at a few more tubes on the Tektronix 570. In the earlier video, when I first introduced this Tektronix Type 570 curve tracer, I showed a couple of tubes, and I'd like to continue with that mainly as a kind of context for understanding a little more about how you can match tubes, how you can measure tubes, how you can gain the data that a design engineer would use to design tube circuits, that is, the electronics surrounding a particular tube or a particular tube type to accomplish a particular circuit function, an amplifier, an oscillator, a mixer, things of that sort. So what you see on the screen is a 6U8. It is the pentode section of the 6U8, which I showed earlier. On the grid B is a 6GH8, and let me point to a few differences. You notice that the GH8 produces a lot more. This is plate current, so it can produce a lot more plate current at zero bias than the 6U8 can. Now, I think I explained in that earlier video that the 6U8 was used in television sets of the 50s as a vertical oscillator and amplifier. That is, it drove the electron beam from top to bottom on the screen. There was also a horizontal amplifier and oscillator that drove it left to right. The 6U8 triode section, which this is a 2-section tube, was the oscillator, and then this would be the power amplifier to drive the yoke. And obviously the 6GH8, which was a later tube developed for the same purpose, has more gain, more transconductance, and so on. So let's take a look at some of those issues or some of those measurements, and that'll give us a little bit of context. Here are copies of the data sheets out of the RCA Tube Manual. On the right is the 6U8 and the improved 6U8A. Notice it's a medium mu, mu is the amplification factor, triode, and a sharp cutoff pentode. The same is true of the GH8, and as I noted, it was developed specifically as a replacement for the 6U8, but a replacement with a little more performance because remember, as picture tubes got bigger, you needed more drive to swing the electron beam. So this was the probably the most popular vertical oscillator amplifier in the late 50s. I think this came out in 58 and quickly supplanted the 6U8 for this purpose. So other than people who are interested in vintage televisions, of what interest are these tubes? Well, I'm going to use them as an example of how to read a data sheet like this. And for that purpose, I'm going to move to, I will come back from time to time to the 6U8, but I'm going to move primarily to the 6GH8. And let's move in a little bit here so that we can see a little better what things are being shown. Now, at the top is a kind of general description, an English description of the tube, what it might be useful for, and you notice it says, used in multi-vibrator type horizontal deflection circuits, employing series heater string arrangements. So it gives you a lot of background about what they intended to use this for. Now, even though it was intended for horizontal, at least when this data sheet was written, it actually wound up being used more in the vertical sections. Part of the reason is that it just didn't have enough oomph in the pentode side to drive the horizontal yokes of the day, partly because of need for extra power to provide boost voltage and high voltage and so on that I won't get into. But nonetheless, the next three have to do with the heater, the voltage and the current of the heater, as well as the warm-up time. Warm-up time is important because you wanted a controlled warm-up time. You didn't want the tubes to come on right away. That would have provided a huge surge in current. So what you wanted were filaments, and a lot of work went into developing filaments. They weren't just a piece of wire stuck in a vacuum tube. The filaments were developed to take a particular current, but to ramp up to their maximum temperature in a period of time, in this case 11 seconds. Okay, then the next section we're going to kind of skip over. It has to do with the interelectrode capacitance. Now these are issues that are of interest to design engineers, but for most of us, just looking at circuits already designed by somebody else, they're not nearly as important. What does become important, though, is when we get down into this section. And here, they're showing a horizontal deflection oscillator using this tube. And first, they list the maximum ratings of the tube, things like the maximum plate voltage, the grid number 2 voltage, and so on. Here is a place where a comparison might be in order. Notice that the triode has a 330 volt maximum plate voltage and the pentode a 350. Contrast that with the 6U8, 330 on the triode unit and 330 on the pentode unit. So the plate voltages are comparable. The difference is when you look at the characteristics. Notice that this is the triode unit. Over here is the triode unit of the 6U8. Now, disregard these curves up here. They are only present on this one and not on the other one. The curves we're interested in are these curves here. Notice that out here at the right, we have 400 volts. similarly here we have 500 volts. So obviously they, the people who did this data sheet felt that the 6GH8 could handle more voltage than the people who did the 6U8. Also, what you find is that the slope of these lines and the spacing between them is different. Now, I'm not going to compare them point for point. What I am going to do is calculate the transconductance, first of the 6U8. And you notice over here, I picked 2 points on the curve that were separated, that were along a given plate line. That is, I think I used 200 volts. And I chose 2 points that were 2 volts apart. This is the -2 volt grid line. This is the 0 grid line. So starting up here, I read that to be about 42. And then down here, I read the 2 volt line to be about 28. So that gave me a figure of 42 minus 28, the change in plate current to the change in grid voltage, and that reads about 7,000 micromhos. Okay, what does the spec sheet say? Well, it says that it should be about 7,500. Let me zoom in a little bit. You might be able to see that a little better. The pentode section, you may not be able to read this. This column is for the triode. This is for the pentode. Should have about 5,000 micromhos. Well, I measured for a 1 volt difference, 15 minus 9. I'm sorry, a 2 volt difference. So that comes out to be about 6,000 micromhos. And it says that the typical is 5,000. Now, one of the things that I'll also mention is these are typical values. Obviously, different tubes would vary. Generally, the value that they would list there was a value that they could pretty much guarantee the tube would have. So, although it's a typical value, it also is generally a minimum value, at least for most tubes. So, let's look then at those same calculations with the 6GH8. Well, I got 32 minus 12 for the same 2 volt difference. That's 10,000 micromhos. Now, I'm going to have to flip over here to show that. This shows a transconductance of 8,500 micromhos. Now that's once again a minimum value. So the 6GH8 that I'm testing is a little hotter than the one that they use for the minimum. Similarly, I'm sorry, that's the pentode unit, 7,500. I told you wrong. This is for the pentode. For the triode, no, I'm right. Reset. 10,000 micromhos for the triode compared to 7,500 or 8,500 on the spec sheet. For the pentode, I calculated approximately 8,000 micromhos, 20 minus 12 divided by 1 volt. And it shows 7,500 as the value. So that is the way, for example, that you calculate using a curve tracer the actual amplification factor of the tube. That is, you pick the plate voltage that you're most interested in. You pick 2 values, or actually, if you do this, you can do a number of values, but you basically take the difference between 2 of these lines and you measure the change in plate current and the change in grid voltage. And then from that, you can calculate the transconductance. Now, you can do similar things for calculating plate resistance and amplification factor. I won't go into those. If you're interested in those, go back and watch my videos on how vacuum tubes work and how and vacuum tube circuits. And I talk a little more about that. Before I leave the 6U8 and the 6GH8 curves, I wanted to mention one more thing, and that is, some of you may be wondering, why do these curves stop at a different voltage? Remember, the horizontal axis is the plate voltage, and the vertical is the plate current. And then these steps represent grid voltage. Well, why, for example, does this curve stop there instead of going out as far as this one, and so on? Well, that is because of the series resistor that is placed in the circuit. And the series resistor is there for a couple of things. One is to develop the voltage, and the second, that is to develop the voltage difference as the signal changes. In other words, it is the plate load resistor. But the reason the series resistor causes this line is the slope of this line from here to there is simply the resistance. Remember, resistance is simply voltage divided by current. So it is E, the horizontal, divided by I, in this case the vertical. So if you calculate the voltage and current that it takes to make this line, let me show you what you get. Measured on the screen, I got an 80 volt change in the plate voltage divided by, this is E over I. I is 8 milliamperes, 0.008. That works out to 10,000 ohms. And, pardon the swinging of the camera here, notice the series load that is set right here is 10K. That is how you get this slope. In other words, the difference between this voltage and this voltage is 80 volts. The difference between this current and this current, that is from here down to here, or actually down to here, is 8 milliamperes. So we divide the 80 volt difference this way by the 8 milliamperes this way, and that is how we got the value of the series resistor. In other words, this can vary. Let me go to a 5K resistor. There you'll notice that the slope is much taller. Let me go to a 20K resistor, and you see the slope is much is further over. Okay, now perhaps we can move on to some other tubes. Well, like all things in life, there are little surprises, and I thought I would take advantage of one surprise while in the middle of setting up for another tube type. The step generator on this 570 stopped, so I have found the problem. It turns out it was just a dirty pin on the step amplifier output tube, the CL6, that I've actually shown you the schematic in an earlier video. But while I had the unit open, I thought it might be an opportunity for me to show you what one of the changes that I made. You notice these capacitors here, that is this yellow one here and the one over there, that I added to suppress oscillation in the step amplifier. Let me show you the schematic of that so you'll understand why I wound up having to do that and my theory about why that fixed the problem. Here is the step amplifier schematic, and the tube that had the bad or dirty pin was this output tube, the 6CL6. The capacitors that I added, one is at the bottom of this resistor, the 120K, which is the minus 300 volt supply. And the other one I added to the plate, which is the plus 400 volt supply. So why did I do that, and what was my theory in adding those capacitors? Well, what those do is they clean up these power supplies, and I think what is going on is the leads, that is the wires, from these two terminal points, which are in that area that I showed you a minute ago where the capacitors are located, that run all the way back to the power supply, are rather long. In fact, they're about 4 feet long by my calculation. And here's one of the reasons I think that that causes a problem and why they need to be bypassed right here, right at the tube. You notice this line, which comes down here and goes over through this set of selectable resistors. This is the switch that sets the number of steps per, let's see, the VCS per step. I guess that's volts, maybe is what that refers to. It's not printed very well there, but anyway. And the way it works is this is a feedback resistor that feeds back to this stage. And then this 6AU6, you notice, it runs through this set of tubes and eventually over to the 6CL6. So basically what you have, I'll back off a little bit here, what you have is a feedback loop that runs around like this. And the loop time through that feedback loop is causes the step generator to oscillate at about 300 or 350 kilohertz. And you can suppress that oscillation by bypassing these supplies, because effectively what you're doing is you are lowering the impedance of the power supply at this point. And that means that a signal that feeds from here through to this supply and then winds up affecting one of these other supplies doesn't get reinforced by this feedback loop. If you've looked at some of my videos on control loops and control theory, you'll understand a little better what we're talking about there. But anyway, that's one of the little changes I had to make to get this scope working again. Initially, I put these in to suppress the oscillation, but the most recent problem was one of the pins. I think it was pin the grid of the 6CL6. What was happening was I was not getting a step waveform on the cathode, which is fed through this switch to the tube under test. But I was getting a signal on this resistor. And at first I thought the 6CL6 was bad, so I took it out and tested it on a tube tester, and it tested fine. I put it back and the scope worked fine. Then I discovered that if I wiggled the 6CL6 slightly in the socket, that the problem would come and go. So my guess is what happened. By the way, I pulled it out and cleaned the pins of the tube again, and since then it hasn't happened, even if you wiggle the tube quite a bit. But I think what happened is, while I was changing the connections for another tube type, I managed to vibrate the scope just enough that the grid pin of this tube, which had oxidized a little bit, stopped making contact. Well, anyway, enough of the diversion. Let's get back to checking tubes. So we're now back with the 6SL7, and this is section 1. This is a dual triode. So this is section 1, and this is section 2. You notice that there's virtually no difference between the two. So these two sections are well matched. I have to make a correction. The tube that I showed you just a second ago was actually the 6SN7. This is the 6SL7. So you see the difference. This is one section, and this is the other. Now, what I'm going to do is put the 6SN7 back in, and then compare it to a 7N7. So here is the 6SN7 back again. Notice the little difference. And now I'm going to compare it first to another 6SN7. And now I'm comparing a pair of 6SN7s. This is the first tube. This is the second tube. Notice that there is more variation here between tube A and tube B than there is between one section of the same 6SN7 and the other section. I'll show you in a second on the tube diagram what I'm talking about. But this is one tube, this is the other. Notice there is a substantial difference in the two, and let me explain that in just a second, but before I do, let me show you what's actually happening down here on the test panel. You see we have two 6SN7s, this one and this one, and we are wired up to one section of this tube and one section of this tube. So that's what you're seeing. So let me show you on the tube diagram what's going on as well. So what we were doing in that second or the last display is notice that there are a pair of triodes. This is called a medium mu twin triode. Mu, of course, is just amplification factor. So twin triode means that in each package, in each envelope, there are two tubes that are driven off the same filament. So what we are doing is, for example, this left-hand side is called triode 1. And so what we're doing is we're comparing triode 1 of one tube with triode 1 of another tube. In other words, I'll use the 6SL7 as an example here. In other words, it's as though we were comparing this section of this tube with this section of this tube. Now, of course, we could set up to do the other section of each tube, or we could compare the left-hand triode of this one with the right-hand triode of that one, and so on. But the way that the 570 is arranged, you can only do two tubes at one time. So you can't, for example, set it up so that you can compare this one with this one and this one with this one, or this one with that one, and so on. You can only do two tubes, but they can be different tubes. So we could, for example, as we did earlier, compare a 6SL7 one section with a 6SN7 one section. So I hope this has been at least interesting for those of you that might be interested in curve tracers, and with the 570 in particular. And this, combined with the earlier video that I did, is going to be the last video. So I hope you've enjoyed it, and I hope that that things will go well for you. Maybe the country will come out of this coronavirus problem better off and stronger than ever. So, as I always say at the end, have a nice day.